Spike energy method for bearing fault detection, innovative approach to identify faults in mechanical bearings. Introduction to spike energy method, background and industrial context, principle of operation, measurement process and instrumentation, severity assessment charts, interpretation of spike energy trends, limitations of the spike energy method, current best practices, engineering use case and maintenance programs, conclusion and engineering perspective. The spike energy method is a classical vibration-based condition monitoring technique widely used for the early detection of rolling element bearing defects. It was developed during the early evolution of predictive maintenance and vibration diagnostics, at a time when computing power and advanced signal processing techniques were limited. The method focuses on capturing and quantifying short-duration, high-frequency acceleration spikes that occur when a bearing defect, such as a crack or spall, is struck by a rolling element. These impact events generate brief bursts of energy that are not always visible in conventional low-frequency vibration measurements. By emphasizing these spikes, the spike energy method provides sensitivity to incipient faults long before they grow large enough to dominate overall vibration levels. From an engineering perspective, the method is valued for its simplicity, repeatability, and ability to provide an early warning indicator of mechanical degradation. It has been implemented in many legacy condition monitoring systems and is still referenced today as a foundational concept in vibration analysis. Although modern techniques such as envelope analysis and spectral kurtosis have largely superseded it, understanding spike energy remains important for engineers working with existing systems or interpreting historical data. This presentation introduces the method in a structured, professional engineering context, explaining its principles, applications, limitations, and best practices for use in contemporary maintenance programs. The spike energy method emerged from early research into shock pulse and high-frequency acceleration measurement techniques used in rotating machinery diagnostics. During the 1970s and 1980s, industries such as power generation, oil and gas, and manufacturing sought reliable methods to detect bearing failures before catastrophic breakdowns occurred. Traditional overall vibration measurements, typically expressed in velocity, were effective for imbalance and misalignment but often lacked sensitivity to early-stage bearing damage. Engineers observed that localized bearing defects produced repetitive impact forces, exciting the natural frequencies of the bearing and surrounding structure. These impacts manifested as sharp, high-frequency acceleration spikes. The spike energy method was designed to isolate and quantify these events by applying high-pass filtering and specialized signal processing. As a result, maintenance teams could trend a single parameter, spike energy, over time and identify abnormal increases associated with defect initiation and progression. This approach was particularly attractive because it reduced complex vibration signals into a manageable diagnostic indicator. However, the method was developed in an era when accelerometers had relatively consistent natural frequencies and analog signal processing dominated. As sensor technology evolved, variations in accelerometer response introduced challenges that engineers must now understand when applying or interpreting spike energy data. Despite these limitations, the method played a significant role in shaping modern condition-based maintenance practices. The fundamental principle of the spike energy method is based on the detection and measurement of impact-generated vibration energy within a high-frequency band. When a rolling element passes over a defect on a bearing raceway or rolling surface, a short-duration force impulse is generated. This impulse excites resonances in the bearing, housing, and machine structure, producing a burst of high-frequency acceleration. The spike energy parameter, often expressed in GSE units, represents the cumulative energy of these spikes over a defined measurement period. To extract this information, the raw acceleration signal is passed through a high-pass filter to remove low-frequency components associated with normal machine operation. The remaining signal highlights sharp transient events. The signal processing algorithm then rectifies and integrates these events to produce a single scalar value. From an engineering standpoint, the method assumes that defect-related impacts are the dominant source of high-frequency spikes and that their energy content increases as the defect grows. This assumption generally holds for rolling element bearings under steady operating conditions. Understanding this principle helps engineers interpret spike energy trends correctly and recognize when increases may be related to bearing degradation rather than external noise or process-related impacts. Accurate spike energy measurement depends heavily on proper instrumentation and measurement practices. An accelerometer is typically mounted rigidly on the bearing housing, as close as possible to the load zone of the bearing. Good mounting, such as stud mounting or a properly prepared adhesive mount, is critical to ensure high-frequency signal transmission. The accelerometer must have sufficient frequency response to capture the impact-related spikes without excessive attenuation. During data acquisition, the acceleration signal is routed through a high-pass filter designed to isolate the frequency range where bearing impacts are most pronounced. The filtered signal is then processed to calculate the spike energy value. Consistency is essential. Measurements must be taken at similar operating conditions, sensor locations, and machine speeds to ensure valid trending. Engineers must also be aware of environmental and process influences, such as cavitation, gear mesh impacts, or electrical noise, which can introduce false spikes. A disciplined measurement process ensures that spike energy trends reflect actual bearing condition rather than measurement variability. The image illustrates a typical legacy spike energy severity chart, showing threshold zones used historically to classify bearing condition. Original implementations of the spike energy method were often accompanied by severity assessment charts that defined acceptable, marginal, and unacceptable spike energy levels. These charts were developed empirically based on specific accelerometer types, machine classes, and operating speeds. Engineers used them as a quick reference to assess bearing health without extensive signal analysis. Typically, the charts plotted spike energy magnitude against machine speed, providing threshold zones for decision-making. While these charts were valuable at the time, their applicability is limited in modern practice. Changes in accelerometer design, frequency response, and sensitivity mean that absolute spike energy values can vary significantly between sensors. As a result, direct comparison to legacy charts can be misleading. Nonetheless, understanding these charts is important for interpreting historical data and appreciating how early condition monitoring programs standardized decision criteria. Engineers should treat severity charts as contextual references rather than absolute diagnostic tools. This image demonstrates how increasing spike energy levels over time can be associated with bearing defect progression. Interpreting spike energy data requires an emphasis on trending rather than absolute values. A gradual and sustained increase in spike energy over time is often a strong indicator of bearing defect initiation and progression. Engineers should look for consistent upward trends that correlate with operating hours rather than isolated spikes caused by transient events. Comparisons should always be made using the same sensor, mounting location, and measurement setup. Sudden step changes may indicate changes in instrumentation rather than machine condition. It is also important to correlate spike energy trends with other condition indicators, such as overall vibration, temperature, and lubrication condition. When interpreted correctly, spike energy provides valuable insight into the early stages of bearing damage, allowing maintenance teams to plan inspections or replacements proactively. Engineering judgment plays a key role in distinguishing meaningful trends from noise. Despite its usefulness, the spike energy method has several important limitations that engineers must recognize. One of the most significant is its dependence on accelerometer natural frequency and frequency response. Different sensors can produce different spike energy values for the same machine condition, making absolute comparisons unreliable. The method is also sensitive to non-bearing related impacts, such as gear tooth contact, cavitation, or external shocks, which can lead to false indications. Additionally, spike energy provides limited diagnostic detail. It indicates the presence of impacts but does not identify defect type, location, or specific bearing components. As machinery and monitoring technology have advanced, more sophisticated techniques have become available that offer greater diagnostic precision. Understanding these limitations helps engineers apply spike energy appropriately and avoid over-reliance on a single parameter. In modern condition monitoring programs, spike energy is best used as a complementary trending parameter rather than a standalone diagnostic tool. Best practice dictates that spike energy measurements should be trended consistently over time using the same sensor and setup. Absolute comparisons to legacy severity charts should be avoided unless sensor equivalence is verified. Engineers are encouraged to combine spike energy data with advanced techniques such as envelope analysis, frequency spectrum analysis, and time waveform inspection. This integrated approach improves diagnostic confidence and reduces the risk of false alarms. Spike energy can serve as an early warning indicator that prompts further investigation using more detailed analysis methods. When applied within a structured maintenance strategy, it continues to provide value despite its age. A practical engineering use case for spike energy is in routine condition-based maintenance inspections of critical rotating equipment. By collecting spike energy data at regular intervals, maintenance teams can establish baseline levels and detect abnormal increases early. This allows planners to schedule inspections, order spare parts, and align maintenance activities with production requirements. Spike energy is particularly useful in environments where quick screening of many machines is required. Machines exhibiting elevated or increasing spike energy can then be prioritized for detailed analysis. This tiered approach optimizes resources and reduces the likelihood of unexpected failures. From an engineering management perspective, spike energy supports risk-based maintenance decisions and contributes to improved equipment reliability. In conclusion, the spike energy method remains an important part of the historical and practical foundation of vibration-based condition monitoring. It provides a simple and effective means of detecting impact-related bearing faults, particularly in their early stages. While modern diagnostic techniques offer greater detail and robustness, spike energy continues to deliver value when used correctly and interpreted with engineering judgment. Its greatest strength lies in consistent trending rather than absolute thresholds. Engineers should understand both its capabilities and its limitations, integrating it with complementary analysis methods to achieve reliable fault diagnosis. By applying the method within a disciplined and professional maintenance framework, organizations can continue to benefit from its early warning capabilities while leveraging modern advancements in vibration analysis.